Hi everyone, this is Kiranmai from H&S department. Today in this session, we are going to discuss about interaction of radiation with matter. Under this topic, we are going to discuss what are the lasers, interaction of radiation with matter, characteristics of lasers, and when a radiation interacts with matter, which sort of process will happen, like stimulated absorption, spontaneous emission, stimulated emission, and from those different processes we are going to derive some coefficients called as Einstein coefficients, and we are going to derive a relation between them. And then at last, using all the above topics, we are going to derive two definite conditions how to get a laser output. Two definite conditions to satisfy to get a laser output. So coming to the lasers, the light emitted from a conventional light source, whatever the light sources we are using in the domestic purpose, are said to be incoherent because the radiations emitted from different atoms do not bear any definite phase relationships with each other. Which means that, for suppose if you take a tube light, which we are using at a domestic purpose, it is the atoms which are producing the light radiations over there, they are not they are not in phase relationship with each other, they are out of phase with each other. So, and they are deviated in all the directions, they are not monochromatic. So all these things comes under the conventional light source, whereas a laser is a thing which is having monochromacity, high intensity, highly directional, and they are coherent with each other. These are the main characteristics of laser which makes it more prominent than a conventional light source. What is a laser actually? It is abbreviated as light amplification by stimulated emission of radiation, where the light will get amplified by a process called stimulated emission. So that output light is called as laser, light amplification by stimulated emission of radiation. Coming to the lasers, these are has been extended up to gamma rays, which means that we can get, by using lasing action, we can produce up to gamma rays, and the lasers which produce these gamma rays are called grazers. And the laser is the outgrowth of maser, which means microwave amplification by stimulated emission of radiation. If the stimulated radiations lies in the optical region, then such type of devices are called optical measures, which otherwise lasers. If the stimulated radiation lies in optical region, which means that whatever the output what we are getting at the output of stimulated radiation, if its output is in the range of optical region, then we can call that device as optical measure or a laser. Coming to the characteristics of a laser, there are four important characteristics for the laser. One is monochromacity, highly directional, highly coherent, and highly intensified. Monochromacity means a laser output, whatever we are getting from the device, it is having only a single wavelength. It single wavelength. So the spread of the order, its wavelength will be in the order of few Armstrongs only, and it will be definitely less than 10 Armstrongs. And lasers emit continuous waves of very long durations. Coming to the directionality, lasers are produced only in one direction as the photons traveling along the optical axis of the system. Coherency means all the radiations which are emitting out of the source will be in phase with each other. The waves emitted from the laser source will be in phase with each other and they are of very same frequency. Whereas conventional light sources, what we are using domestically, they are emitting random wavelengths with no common phase relationship with each other. As I told you earlier itself, conventional light sources produce radiations in all directions with all the wavelengths, and there is no common relationship between them. They are out of phase with each other. So that's why lasers are more prominent because of this coherency property, that these lasers have a definite phase relationship between them, and they will have same frequency or wavelength which are emitted of same light source. Coming to the intensity, As laser beams are emitting in single direction, all the radiations will be propagating in the form of a plane wave. So the definitely energy will be concentrated in a very narrow region. Hence, the intensity is tremendously high. And it is estimated that light from a typical 1 megawatt laser is 10,000 times brighter than the light from the sources at the Earth's surface, which means that whatever the laser source which is having a typical power estimation of 1 milliwatt, it will produce 10,000 times brighter light than from the sources which we are using on the Earth's surface. Coming to the divergency, as I told you, laser is having a main property of coherency and directionality. Directionality means all the radiations which are emitting from the source will move in single direction. So obviously its divergence angle will be very less comparable to a conventional light sources. Divergency or angular speed of laser beam is extremely small. Coming to the interaction of radiation with matter, uh, to to verify how a radiation interacts with a matter, let us consider one matter which is having a number of atoms arranged in a regular manner. Now consider a radiation which is interacting with this matter. For interaction, first of all, the energies of the energy of the interacting photon should match the energy difference between the two states of the atoms which are involved in the interaction. So for that, let us consider the material which is having two energy levels, E1 and E2. Now, when this radiation interacts with that matter which is having two energy levels, E1 and E2, there are three chances of processes happening. There are stimulated emission, stimulated absorption, and spontaneous emission. Coming to the first process, stimulated absorption, if the radiation is having an energy which is comparable to the energy difference between the two energy levels of the atoms which are involved in the interaction, then obviously when this photon or a radiation of energy E interacts with the atom which is in the lower energy level, the atom absorbs that energy and get excited from lower energy level to higher energy level. As the atom is getting stimulated due to the interaction of radiation, the process is called stimulated, and here the energy is absorbed by the atom, hence the process is called as stimulated absorption. And initial state, the atom will be in the lower energy level. Once the stimulated absorption process happens, in the final state, atom will get excited to second energy level or a higher energy level. So if the radiation interacts with the atoms in the lower energy state, the atoms absorb the energy and get excited to higher energy state E2. This process is called as stimulated absorption. Second one, stimulated emission. So stimulated emission means here also the process will happen by taking the help of external energy. For suppose when a atom is in the excited state, where it will stay for its lifetime. So before the completion of its lifetime, if this atom is interacting with a radiation, then what happens due to the stimulation of this radiation, the atom will de-excite to de-excite from higher energy level to lower energy level by emission of two photons. Those two photons will be, one of them will be the incident photon, another will be due to the de-excitation of atom from higher to lower energy level. So in a stimulated emission process, we will at the output we will get only we will get two photons which are coherent with each other, moving in the same direction and having same frequency. So such type of two photons, we can call them as coherent. So in stimulated emission, if the radiation interacts with the atoms which are already in the excited state, then the atom comes to lower energy state, occurs with the emission of photons of energy. This process is called as stimulated emission. The third process, that is spontaneous emission, in this process happens only when the completion of lifetime is done. For suppose an atom is there in the upper energy level, where it stays there for high stays there for its lifetime, which is about 10 power minus 8 seconds. So after that completion of that lifetime, the atom randomly or spontaneously comes back to lower energy level by emission of one photon. So such process we will call it as spontaneous emission, where there is no external energy is required. Once the lifetime is completed, atom automatically come back from the higher energy level to lower energy level by emission of photons. So in this process, atoms in the excited state drop to the lower energy state after they have stayed in excited state for their lifetime. During this process, photon of energy has been emitted, and the lifetime of particle in the excited state is in the order of 10 power minus 8 seconds. So there exists some excited states in which the lifetime will be much greater than 10 power minus 8 seconds. Such states are called metastable states, and the lifetime of metastable states about 10 power minus 3 seconds. So what are normal states and metastable states? Normal states are nothing but a higher excited states which are having a lifetime of about 10 power minus 8 seconds. Such states we can call it as normal energy states. Whereas if some states which are having more lifetime comparable to the normal energy states, about 10 power minus 3 seconds, then such states we can call them as metastable states. And the probability of having stimulated emissions is more in metastable states, whereas probability of having spontaneous emission is more in normal energy states. As normal energy states is having lesser lifetime, obviously atoms automatically de-excite from higher energy level to lower energy level very easily by emitting a single photon. Whereas when coming to the metastable states, as the lifetime is more comparable to a normal energy state, atoms will stay there for longer time. So the probability of interacting with the atoms with the higher energy state is more in metastable states. Definitely the atom de-excites by emission of two photons. One is the incident photon, another one is the photon which is due to the de-excitation of atom from the higher energy level to lower energy level. So Einstein coefficients and their relations. How would you define Einstein coefficients? How would we derive Einstein coefficients? For that, we should have a clear-cut idea about what is a stimulated absorption, what is spontaneous emission, and what is stimulated emission. So for that, as we had considered two energy states in the before topic, that is spontaneous emission, spontaneous stimulated emission, and stimulated absorption, let those energy levels be E1 and E2, which are having the atoms N1 and N2. So the energy of the incident photon be h nu. So what are the considerations we are taking here? We are going to consider N1 number of atoms per unit volume in E1 energy level, and N2 number of atoms in per unit volume in E2 energy level. So let N be the number of photons per unit volume with a frequency nu, then energy h nu is equal to E2 minus E1, and the energy density of interacting photon be rho nu is equal to nh nu. So according to stimulated absorption, this happens only with the aid of external energy. When a radiation interacts with the atoms in the lower energy level, then only this process will happen. So stimulated absorption rate depends on the number of atoms in the lower energy level and also the intensity of incident radiation. So together, if you write it, it is proportional to the product of N1 into rho nu. So if you remove the proportionality, you have to place one constant that is called B12, which is an Einstein coefficient of stimulated absorption. Einstein coefficient of stimulated absorption. Why B12 means as the process is happening from first energy level to second energy level, we are going to denote that constant as B122. And B12 is called as Einstein coefficient of stimulated absorption. Second process, once the atom reaches the higher energy state, after their lifetime, they move back to their lower energy level spontaneously. Here, there is no need of any external energy. So therefore, the spontaneous emission depends only on the number of atoms in the excited state. Therefore, spontaneous emission rate is proportional to number of atoms in the second energy level, that is N2. Again, if you remove the proportionality, you have to place one constant. That constant is represented with a letter A21, where A21 is called as Einstein coefficient of spontaneous emission. As the process is happening from second to first energy level, we are representing the constant A with 2 to 1. Third process, where before the de-excitation itself, if the atom in the second energy level interacts with a photon, then the stimulated emission will happen. So its stimulated emission depends on the number of atoms in the higher energy level, with that the energy of interacting radiation. So it will be the product that is proportional to the product of N2 into rho nu. Again, proportionality, removal of proportionality, we have to place one constant, that is B21, where B21 is called as Einstein coefficient of stimulated emission. As the process is happening from second energy level to first energy level, we are calling that constant as B221. Now, from equilibrium condition, always upward transition rate will be equal to downward transition rates. Out of the three different processes, whatever we are discussing here, spontaneous emission, stimulated emission, and stimulated absorption, in these three different processes, one is an upward transition, another two will be a downward transition. So upward transition rate, that is stimulated absorption rate, is equal to sum of spontaneous emission rate and stimulated emission rate. So rho nu n1 b12 is equal to this is stimulated absorption rate, that is equal to stimulated emission rate plus spontaneous emission rate. Now just rearranging the terms and getting an expression for rho nu, that is density of incident radiation, A21 N2 by N1 B2 minus N2 B1. Now from this, just take a common of N2 B1, and N2 B1 and N2 N2 will be cancelled out in this, and you are left with A21 by B21 divided by N1 by N2 into B12 by B21 minus 1. We are just going to compare this expression with Planck's law, sorry, Maxwell-Boltzmann law. Using Maxwell-Boltzmann law, we are just going to change this expression as Ni is equal to N naught Zi exponential minus Ei by Kt. Just rearranging what is N1, what is N2. N1 in place of I, just replace with 1. So N naught G1 exponential minus E1 by Kt. And in place of I, just replace it with 2. You'll get N naught G2 exponential minus E2 by Kt. Then again N1 by I2, N2, if you find out the ratio of number of atoms in first energy level to number of atoms in second energy level, you'll get G1 by G2 exponential E2 minus E1 by Kt. Just replacing this expression in the above density formula, you'll get a final expression like A21 by B21 into G1 by G2, B1 by B12 by B21 exponential E2 minus E1 by Kt minus 1. Now compare this expression with the Planck's law of black body radiation. You'll get the rho nu is equal to numerator is 8 pi h nu q by c cube, and denominator is exponential E by Kt minus 1. So if you compare these two expressions, the numerator term A21 by B21 is equal to this term, and the coefficient of exponential term G1 by G2 into B12 by B21 will be equal to 1. Now comparing them, you'll get the final expression like G1 by G2 into B12 by B21 is equal to 1, and A21 by B21 is equal to 8 pi h nu cube by c cube. These two relations are called as Einstein relations. Now, depending upon these spontaneous emission rate, stimulated emission rate, and stimulated absorption rate, we are going to derive two conditions for emission of lasers at the output. In that, the first condition is the ratio of spontaneous emission rate to stimulated emission rate. Just taking the ratio of spontaneous emission rate to stimulated emission rate, cancelling N2 and N2, you'll get A21 by B21 rho nu, where A21 by B21 is nothing but exponential h nu by Kt minus 1. So if you take this one as a thing, spontaneous emission rate predominance, which means that if you want to have more spontaneous emission rate, so as we had discussed, as we had taken the ratio of spontaneous emission rate to stimulated emission rate, it is inversely related to rho nu, that is intensity of incident radiation. So to make spontaneous emission rate lesser and to make stimulated emission rate more predominant, just we have to make rho nu as a larger value, so that the stimulated emission rate will be higher than a spontaneous emission rate. So to get laser output, we need stimulated emissions. So to have more more stimulated emissions, the intensity of the incident radiation should be large, then only we will get more stimulated emission rate than a spontaneous emission rate. Second condition, stimulated emission rate to stimulated absorption rate. Here, if you cancel rho nu and rho nu, you'll get N2 by N1 into B21 by B2, B12. So Q is proportional to N21 by N1, which means that if N2 is greater than N1, if N2 is greater than N1, then only more stimulated emission rates will happen comparable to comparable to stimulated absorption rate. So to have more stimulated emissions, to have laser output, stimulated emission rate should be high. To have more stimulated emission rate, the number of atoms in the second energy level should be greater than the number of atoms in the first energy level. This condition is called as population inversion. So to achieve more number of stimulated emissions, population of excited state should be greater than the population of lower energy state. The condition is called as population inversion. So what are the two conditions we got from these two cases? That is, first case, increase of energy density of interacting radiation, and the second one is to create population inversion. If these two conditions can be satisfied, then we can get a laser at the output due to stimulated emissions. Thank you.